Ever look at the world and wonder about the hidden rules that make everything go? You know, from a simple thrown ball to a planet circling the sun? Well, today we're pulling back the curtain on the physics of motion. We're going to start with a question that sounds simple but is actually kind of tricky, and by the end you'll be seeing the world just a little bit differently. Let's dive in. So let's start with you. Right now, are you moving? Your first thought is probably, nope, I'm sitting still. But what if I told you that you're also hurtling through space on this planet at about 67,000 miles per hour? The answer, it turns out, really depends on your point of view. And that gets to the heart of a huge idea in physics called relative motion. Think about it this way. If you're on a train, you're not moving at all compared to your seat, right? But for someone standing on the platform watching you go by, you're just a blur. So motion is never absolute. It's always compared to something else. That's our first big idea. Okay, so if we want to talk about motion like a physicist, we need to learn two really basic concepts: scalars and vectors. You can think of them as the two different languages we use to describe how things move. And trust me, understanding this difference is the key to everything else we're going to talk about. First up, we've got scalar quantities, and these are super simple. A scalar just tells you how much of something there is. That's it. When you say it's been 10 minutes, or a bag of sugar has a mass of 2 kilograms, you're using scalars. It's just a number, a magnitude, no direction needed. But then we have vectors. And vectors are a little pickier. They have a magnitude, the how much part, and they have a direction. It's not enough to say you're pushing a box with some amount of force. You have to say you're pushing it forward. That direction is what makes it a vector, and it's a huge deal. So let's put them side by side. See? Words we throw around all the time, like speed and velocity, are totally different things in physics. One is a scalar, it just cares about the number. The other is a vector, it cares about the number and which way it's going. And this isn't just being picky about words. It completely changes the math, as you're about to see. So let's put this whole scalar versus vector idea to the test. We'll start with our first big matchup, the tale of two paths: distance versus displacement. Distance is pretty much what you think it is. It's the total ground you cover. The best way to think about it is like the odometer in your car. It doesn't care if you went forwards, backwards, or in circles. It just keeps adding up every single meter you travel. It's a scalar, just a number that always goes up. Okay, look at this. Imagine you're driving along this beautiful winding road. You follow every single curve from point A to point B, and by the end, your odometer says you've traveled 8 kilometers. That's your distance. Pretty straightforward. Now, displacement. Displacement is a whole different beast. It could not care less about the scenic route you took. Displacement only cares about two things: where did you start and where did you end? It's the straight line between those 2 points, what they call the as the crow flies measurement. And because it has a direction, it's a vector. And here's the punchline. Even though you drove that long 8-kilometer journey, your displacement is just 2 kilometers to the east. See the massive difference? The distance was 8 kilometers. The displacement is 2. One is the journey, the other is just the direct result. Yeah, this is a classic stumbling block when you're learning physics, but it's really that simple. Distance is the long, winding road, displacement is the straight line shortcut, and now you're in on the secret. All right, so we've figured out the path something takes. The next obvious question is, well, how fast did it go? And this brings us to another famous pair that people mix up all the time: speed and velocity. And no surprise here, the difference between them goes right back to our scalar versus vector rule. Speed is the scalar. It's all about the total distance you traveled divided by the time it took. But velocity, our vector, is all about your displacement divided by time. The formulas look almost identical, but that one different word, distance versus displacement, makes all the difference in the world. Using a different input can give you wildly different answers. Let's look at a perfect example of this. Okay, check out this classic physics puzzle. We've got a swimmer, Usha, in a 90-meter-long pool. She swims all the way to the other end and immediately turns around and swims right back to where she started. And she does all of that in just 1 minute. She's obviously moving pretty fast, but what's her average velocity? Let's break this down. Her speed is easy to figure out. She traveled 90 meters there and 90 meters back, so that's 180 meters. She did it in 60 seconds, so her average speed is a respectable 3 meters per second. But what about her velocity? Well, remember, velocity is based on displacement.
And since she ended up exactly where she started, her displacement is 0. And 0 divided by 60 seconds is a big fat 0. So she was swimming like crazy, but her average velocity was 0. How wild is that?
So we know things can move with a certain velocity. But what happens when that velocity changes? What do we call it when you hit the gas, slam on the brakes, or even just take a turn? That, my friends, is where acceleration comes in.
At its core, acceleration is just any change in velocity. And since velocity is a vector, meaning it has both speed and direction, you can actually accelerate in 3 different ways. You can speed up, you can slow down, or you can just change the direction you're going. All 3 are acceleration.
When you're speeding up, like a car when the light turns green, we call that positive acceleration. When you're slowing down, like an airplane hitting the brakes after landing, that's negative acceleration. You'll sometimes hear it called retardation or deceleration, but both are just types of acceleration, because in both cases, your velocity is changing.
So how do we tie all of these ideas together? How can we see the whole story of an object's motion at a glance? Physicists love to use a powerful tool, graphs. Now, I know they can look a bit intimidating, but they're amazing at telling a story. Let's decode them. Okay, first, let's look at a distance-time graph. So distance is on the vertical axis, time is on the horizontal. The most important thing here is the slope of the line. If the line is a straight diagonal line, that means the object is moving at a constant speed. The steeper the line, the faster it's going. And if you see a curved line like that, that means the speed is changing, it's accelerating. Now, let's switch over to a velocity time graph. Here, things are a little different. A flat horizontal line doesn't mean it's stopped. It means the velocity is constant, so 0 acceleration. But if you see a straight line sloping upwards, that tells you the object is speeding up at a steady rate. That's uniform positive acceleration. See how each line tells a completely different story?
And that brings us to our final thought. Let's say you're driving and you take a corner. Even if you keep your speed exactly the same, you are accelerating. Why? Because you changed your direction. And if you change your direction, you have changed your velocity. And any change in velocity is, by definition, acceleration. The physics of motion is hiding in plain sight all around you. Next time you're out and about, see if you can spot it in action.